So thanks very much for the kind introduction. Can everybody hear me at the back?
Yes.
Good. So it's really exciting to see so many people enthusiastic about learning about the physics of cycling. It's really nice to be here. And it's also really nice to be able to try and kind of directly provide a service to the taxpayers who fund the ridiculous, unintelligible research which I do in my ivory tower all day. So I'm a physicist. I'm a PhD student at the Centre for Quantum Photonics at the University of Bristol, up on top of the hill. I spend most of my time thinking about and building machines to study the quantum mechanical behavior of light. So quantum mechanics is this theory which really well describes the behavior of small things, single atoms, single electrons, single molecules, things like that. And this theory allows for some really very strange, counterintuitive, bizarre behavior. And what I do is build machines like this. So this is something which sits in a dark lab at the university. We take single photons, single particles of light, and we chuck them into this box. And using this box, we can kind of examine and study and play with these strange, counterintuitive quantum mechanical phenomena. So when I'm not sitting in a dark lab doing this, I spend lots of time thinking about bikes, building bikes, playing with bikes, looking at bikes on Gumtree, all this kind of thing. And why do I love bikes so much? So bikes are really, really fun. Bikes are powerful. They're kind of enabling. They enable us to do more things more efficiently, faster, and so on. And I also think that bikes are kind of intrinsically interesting, just as a kind of toy mechanical system. And I'm going to try and convince you, first of all, that bikes are efficient and powerful and useful, and maybe talk a bit about why that is. And secondly, I hope to convince you that bicycles really are interesting as a machine themselves, as a kind of mechanical system, and that they should be interesting to physicists right now on the cutting edge of research. So why are bikes so powerful? Why are they so efficient? Why do they enable us to do so much stuff? Well, a good starting point is this graph. So this is a famous graph. It was published, first published in Scientific American. And this is basically a graph showing the efficiency of various mechanical systems. So some of these systems are kind of animals. We've got some human beings down here and some machines made by human beings. And here on the y-axis, we've got basically a measure of how much energy these systems have to burn per kilogram to move a given distance. So as we go up this axis, these systems are having to burn more energy, and they're becoming less and less efficient. This is a log axis, so every step we make on here, we reduce in efficiency by a factor of 10. So we're a tenth as efficient, a hundredth, a thousandth, and so on. Here on the x-axis, we just have the mass, the weight of these objects. So up here in the top left-hand corner, we've got things like flies and small rodents, which are very small, very lightweight, but they're also not particularly efficient at turning their energy into distance, into forward motion. Here in the middle, we've got some slightly larger. We've got some larger rodents, birds, and things like this. And down here in the right-hand corner, we've got big, heavy things like cows and humans and cars. These things are large, but they're also very efficient. The one that we really care about is this point right down here at the bottom of the graph, a human on a bicycle. It's the most efficient point on the graph. And from this, we would like to conclude that bicycles are the most efficient machine in the universe. Everybody should ride bicycles all the time, forever. And that's not actually too far from the truth. So a human being on a bicycle is traveling something like 3 or 4 times faster than a pedestrian, but they're burning 5 times less energy in the process. A bicycle is kind of like an amalgamation of some of the most efficient and beautiful, simple machines, mechanisms that humans have ever designed, all piled into a single device. So why are bicycles so efficient? Why do they sit at the bottom of the graph there? A good starting point is this tennis ball. This is a tennis ball traveling somewhere in deep space, many light years away from Earth. And it's drifting through deep space. So we know from Newton's first law of motion that for this tennis ball to change the way in which it's moving, so at the moment it's moving, it's drifting through space. In order for it to change its motion, there needs to be some force. Something needs to poke it. An alien needs to come out of a spacecraft and give it a shove, or it needs to come into the gravitational field of a planet or something like that. If none of that happens, it's just going to carry on drifting through space forever. And this is kind of like the natural behavior of an object in our universe. But it's also contrary to our everyday experience. If we throw a tennis ball or push a bicycle or anything else on Earth, we're familiar with the idea that these things come to a stop pretty quickly. If you want to keep them to keep going, you have to make some effort. Why is that the case? Why can't we live in this world where we coast forever? Why do we have to keep pushing our pedals around? Why do our knees hurt? So here's a model of a not particularly good vehicle. This is a brick, which our friend here is trying to grind across the surface and ultimately up a hill. So we're very fortunate on the planet Earth that we have this wonderful atmosphere, which blankets our blue sphere, which we live upon. We've got some nitrogen and oxygen and carbon dioxide and stuff floating around, keeps us alive, but unfortunately for this chap, it also crashes into the front of his brick as he slides it across the surface. So another thing that Newton told us is that for every force, there is some other secondary force which points in the opposite direction and is just as strong. So this fellow is pushing his brick forwards. He's pushing it into these some of the molecules in the air, and he's trying to push them this way. And a basic law of nature is that there is some force acting on his brick in the other direction. Because of that force, if he wants to keep his brick moving in exactly the same way that it already is, in much the same way as the tennis ball, then he needs to cancel out that air resistance. He needs to cancel out the force applied by the air. So he needs to keep making some kind of effort if he wants his brick to keep moving the same way that it already is. Secondly, he's trying to grind this brick across some flat surface. There's some interaction between the bottom surface of the brick and the ground. He hoped that there would be, otherwise this brick is going to descend into the belly of the Earth. However, this interaction is messy, it's complicated. The ground is rough, there's bits of gravel and sand, and as he grinds this brick along, he's going to be moving bits of gravel around, heating up the bottom surface of the brick, and basically wasting energy into the ground. And there's some associated force with that, which again he has to continuously overcome. So he's really starting to sweat at this point, and if he wants to take it up the hill, then of course he also has to overcome the force of gravity if he wants to make his brick move up a hill. This is a model of a vehicle which is slightly more similar to the kind of thing that we're hopefully going to end up talking about. So this is a wheeled vehicle. First of all, we just simply change our terminology slightly. We start talking about the rolling resistance. We have a wheeled vehicle, we're trying to roll our wheels across this surface, and there's some resistance associated with that. Where that comes from, we'll go into a bit more detail in a bit. Of course, we still have air resistance in exactly the same way as before. And we also have a new threat, which is that here we have some kind of motor, this human being who's making an effort and sweating. But in order to couple his effort into forward motion of the vehicle, we have to go through some mechanism, and there's some kind of mechanical loss, some mechanical inefficiency associated with that coupling. So we've got rusty bearings and a rusty chain, and he's having to grind the pieces of rust in his chain and heat up the oil in the bearings and heat up the metal and so on, and he's wasting energy there and having to work harder. So specifically for bikes, we have one very clear advantage to begin with. So going back to the example of the tennis ball, if we want to change the motion of the tennis ball, we have to apply some force. Normally, our bikes start off like this one, they're stationary, and we'd really like them to be moving somewhere. If we want to change the motion of this bicycle, we have to apply some force, and Newton tells us that the amount of force, the amount of effort we have to make, is related to the mass, the weight of this thing. Bicycles are extremely light. I did a sort of rough calculation earlier. If you imagine taking a standard bicycle and filling all of these voids, all of the tubes, all of the wheels, etc., and sort of roughly filling this thing out with the same alloy that's used to make the frame and the wheels and so on, then this thing is going to be roughly 100 times heavier. So bicycles are very, very roughly 99% air. That makes them very light, and therefore it means that we can accelerate them up to some speed without an awful lot of effort. How can we get away with having something which is so light? Why does it remain strong? Well, that's pretty much an entire mechanical engineering degree. I'm not going to go into an awful lot of detail, but one point that we can quite easily address is that, first of all, most bicycles are made of, well, 2 or 3 triangles, depending on how you look at it. And triangles happen to be very, very strong. Why are triangles very strong? Well, if you look at this thing, this is the only polygon. The triangle is the only polygon where if I want to deform this shape, if I want to bend it or twist it or change its shape in some way in this 2D plane, the only way I can do that is by changing the length of one of these edges. Okay. I can't do it simply by changing the angle at these corners. With the square or any other polygon, that doesn't hold. I can change the shape, I can deform this square just by shifting this top edge over. All the edges remain with the same length, and just these angles change. It's much easier to engineer a rod which is stiff and reluctant to be stretched or compressed than it is to engineer a joint which is reluctant to change its angle. So here's our friend, and she's moving through the atmosphere of the Earth. Here are some bits of, I don't know, nitrogen and oxygen and all sorts of stuff. And maybe she's cycling through this atmosphere at some rate. And in doing so, she's pushing these molecules out of the way, and she's experiencing some force which is requiring her to make some effort to overcome it. If she travels twice as fast, then in 1 second, she's going to encounter twice as many molecules. Twice as many molecules are going to crash into her face, but she's also going to feel them striking her twice as fast. Okay, so in going from a given speed to double that speed, she's going to experience four times the force. And in general, we have this fairly good approximation that the amount of extra work that you have to do goes quadratically, roughly speaking, with your speed. So if you double your speed, you have to make 4 times the effort. And here's an equation which you're not obliged to read, but you can see that there's an A on the end. That's the cross-sectional area. The amount of effort that you have to make is also linearly related to essentially how big you are. So if I carry a great big piece of chipboard and try and run a marathon, I'm going to have to work a lot harder because I'm crashing into an awful lot more air. We have a considerable advantage in that sense with bicycles because they can present such a small cross-section or face to the atmosphere. This isn't a completely fair example because there's no rider on the bicycle, but I think we can agree that this is at least better than this. And you can kind of illustrate that scaling of the air resistance by looking at the comparison of a cyclist on a fast road bike on a smooth road traveling fast and a mountain bike on some rough ground traveling quite slowly. So for the road bike, air resistance gives rise to roughly 20% of the effort that this cyclist has to make, whereas rolling resistance, the effect of the tyres on the road only contributes about 20%. The converse is true for the mountain bike, very roughly. Okay, so before we had carbon fiber road bikes and full suspension titanium mountain bikes, we had these guys. This is a dandy horse or a bone shaker. This is kind of what I see as the next step after a brakeless fixed gear. This is a brakeless, crankless, drivetrainless, single speed with a wooden frame, wooden wheels, and iron tires. So if you were an aristocrat, kind of in the 1800s in Europe, then it was very fashionable to get hold of one of these, basically try and ride it downhill, preferably with no hands, preferably with your eyes closed, and these things were banned numerous times, basically because people ran over too many peasants. So these, as I said, these things have an iron ring in the place where we would normally have our nice pneumatic tyre. That will have actually improved the rolling resistance of these things because the iron can be quite nice and smooth. But of course it gives an incredibly harsh ride, and these things were horrendously uncomfortable to ride around, hence the name the bone shaker. Nowadays we have these nice systems invented by Mr. Dunlop, who's a Scotsman. He was watching his son ride a tricycle prior to the invention, of course, of these things, and his son would get headaches basically riding this tricycle around and bumping up and down. So he invented this thing. This is it's a pneumatic sausage which you wrap around your rim. It's got some kind of rubber membrane which is filled with air under high pressure. And these things work really, really well at making the rides more comfortable. Why is that the case? So a good way to illustrate the advantage of a pneumatic tyre is to draw a comparison with airless tyres. So every now and then someone tries to bring to market the airless tyre, or a tyre which will never get punctures, a tyre which you never have to pump up. Generally these things are made of some kind of foam rubber with a whole load of small air bubbles inside, which aren't necessarily pressurised with a pump. And they promise that you'll never have to fix a puncture ever again. So if you consider the example of a normal pneumatic Dunlop-style tyre, then you have all of this air in the tyre, you run over some bump, and a small section of the tyre is compressed. And the volume of the tyre is then reduced. So if we sort of imagine chopping this tyre up into 10 sections, and the bump which we go over is about the size of one section, then our volume goes from 10 sections down to 9. The relative change in volume is quite small. If we consider this model of an airless tyre, so this is an airless tyre where we have lots of segments which are completely separate from one another, separated by some kind of membrane, then the only part of the tyre which really contributes, or which is really affected by this bump, is this local section here. If this local section is compressed by some bump, then its volume goes from 2 sections down to 1 section. And so that's a much larger relative change in volume. We know from basic thermodynamics, or you can take my word for it, that pressure is proportional to 1 upon the volume. So if we have a much larger relative change in volume here, we end up, over here, then we end up with a much larger relative change in volume, relative change in pressure in this system. What that ends up doing is that if you look at the change in pressure of your tyre as a function of the size of a bump, for a nice pneumatic tyre, standard tyre, it's roughly linear. So the change in pressure in the tyre is roughly proportional to the size of the bump, up until the point where you go over such a large bump at such a high speed that you crash your rim into the ground and destroy your wheel. In the case of the airless tyre, it becomes much more nonlinear. Yes. So to begin with, the airless tyre is somehow a bit softer. The change in pressure is smaller as a function of the size of the bump. But it suddenly increases. There's this kind of wall. And this ends up giving a kind of rougher ride, arguably a worse ride, and arguably less efficient. So we have these really nice tyres. They're really comfortable. They greatly improve the quality of the ride over these iron rims. But they, of course, contribute to our rolling resistance. So as you roll your Dunlop pneumatic tyre across the ground, you're bumping over bits of gravel and sand and all sorts and tarmac, and you're compressing the tire and changing its shape and stretching it and squashing it, and you're basically kneading it like a piece of bread. And we know very well, this chap here knows all too well how hard it is, what hard work it is to knead bread. You heat the bread, you put a lot of energy into it, and ultimately you end up being, well, losing some efficiency of your vehicle. So the dandy horse had bearings. So bearings are the piece of the wheel which hold the wheel in place while allowing it to rotate about an axis. And the dandy horse had bearings which were basically a tube of brass. And they take another rod of brass and stick it through the tube, and then they take some oil which was derived from lamb's wool. They'd have some kind of vessel which would sit next to the bearing and continuously feed lamb's wool oil into your brass rod and cylinder to try and lubricate it and keep it running smoothly. This is a slightly more advanced technology. So this is a drawing from the 15th century by Leonardo da Vinci, and it's a ball bearing. And what you can see is that we have some kind of inner ring, which in our case is coupled to the fork or the frame. And we have bearings arranged around it. These are spheres, just balls, which are arranged around that inner ring. And then we have a second outer ring, which is helping to hold those bearings in place and is also able to rotate smoothly with respect to the inner ring. This outer ring then is coupled to the spokes and the rim of our wheels. And you can see that the amount of contact surface in these things can be very small. Ideally, you put some oil in these gaps and lubricate the whole thing, and it can be many orders of magnitude more efficient than the bearings in a bone shaker. So Leonardo da Vinci kind of was drawing those things in the 15th century, but it wasn't until 1869 that they were actually patented. They were patented by a Parisian bicycle mechanic, and in the same year, 1869, they were used on the bicycle which won what is arguably the very first bicycle race. I think this is the winner. This is his bicycle. He did 70 miles in 10 hours. 70 miles in 10 hours. That's more like it. Okay, so we have this beautiful machine, this amazing machine. It's incredibly efficient. It's full of all sorts of marvels of engineering. It's got these tiny little contact patches. It barely touches anything. The bearings inside here are barely touching anything. And part of the reason that we can get away with this is that this whole thing, this whole machine is basically a collection of components which are just arranged in a sheet, in a plane. That's part of the reason we have such low, well, that's more or less exactly the reason we have such low air resistance. How can we get away with building something like this? This is ridiculous. Why is it? It's a planar machine. How can we balance this thing? How can we drive it around? Why are bicycles so stable? So a natural thing to think is that maybe the answer is that it's humans. Humans have got this incredible supercomputer sitting inside our skull. We've got control systems and learning algorithms and parallelism and all sorts of exciting computation going on inside this thing. We've got incredibly precise and sensitive muscles and feedback systems. Maybe the fact that we are these amazing machines is what enables us to pilot this flat piece of equipment. So the way that you normally keep your bicycle stable is something like balancing this stick. So if the stick is going to lean over to the left-hand side, then I bring the bottom end of the stick underneath the center of gravity and right it. Okay, and we do something kind of similar with a bicycle. So if our bicycle is leaning over to the right-hand side, and we're about to fall off over to the right-hand side, then when we learn to ride a bike, what we kind of learn to do is to steer into the turn and turn the handlebars to the right. And in doing so, as we're moving along, our bicycle comes upright again. Okay, and we just kind of learn to do this. And maybe inside our brains we have very finely tuned control systems which allow us to get that just right, such that our bicycle ends up staying upright. And that's a good hypothesis and a reasonable thing to think. But there is a counterexample, or at least a good reason to think that that's not the end of it. So I took this bike here down the road this morning for an exciting session of bicycle smashing. So this is down in St. Werburgh's this morning. And I'm sure you've seen this before, that you can somehow get your bicycle to happily roll along for a surprisingly long way. Seems like it's at least a bit more stable than a flat sheet of MDF. But there's something really amazing, which I was surprised that I actually managed to film this morning. So at some point, you'll see that I hit the saddle and push the bike off balance there. And this thing just happily rights itself, brings itself back on track and carries on cycling. I'm going to play it a bit faster. I'm proud of it. So that's really kind of remarkable to me. And it suggests that there's seemingly something about the design or the geometry of a bicycle which is enabling it to be more stable than a sheet of MDF. And maybe it's more than just humans having nice brains which allows a bicycle to be ridden. And actually you can kind of test that hypothesis by building bicycles which don't exhibit that behavior, which don't right themselves, which aren't self-stable. And it turns out that they're pretty hard to ride. So you have some kind of inkling that there's something more complicated going on than just a human being being good at riding a bicycle. So what's going on? What's the source of that self-righting behavior? Well, a really good hypothesis is that maybe it's some kind of gyroscopic effect. So if you have this child's toy, a hoop and a stick, and you poke your hoop and it rolls along, if you are rolling your hoop at an appropriate speed, it seems to be somehow stable. It seems to be reluctant to fall over. It seems to hold itself in one specific plane. Again, with a spinning top, if you spin your spinning top up nice and fast, then again it's reluctant to fall over sideways. Even though it's sitting on a sharp point, it has some kind of added stability due to the fact that it's spinning. So we can test that kind of very simple gyroscopic argument by, first of all, locking the fork of the bicycle. So I've just put a skewer through here and prevented the fork from turning. So there's no chance that the bicycle is going to turn the fork at all. And we're just going to hope that the gyroscopic effect, the fact that this wheel is spinning around nice and fast, is going to keep the bike stable as it moves along. Basically, it doesn't work. I'm afraid I don't have film of it, but you can find film of people doing this, and it really doesn't work. It basically falls over exactly as fast as it would fall over if you just pushed it from stationary, or you set it off balance while it was stationary. This guy also tested that idea, so he I should explain one more thing. So maybe it's more complicated than that. So in the first case, we lock up the steering and push the bike and it falls over, and we say, oh, it's not the gyroscopic effect. Maybe it's a more complicated gyroscopic effect. So let's take this apart. So if we have a wheel and we spin it up, then the first thing that we notice is that as you spin it faster and faster, it becomes more and more reluctant to be shifted out of the plane in which it's currently spinning. That's roughly how a gyroscope works. So you can spin up a gyroscope and sit it at some strange angle, and it will happily stay there because it's spinning. But there's a secondary effect. So if I spin this wheel, first of all, I feel that it's reluctant to move. But also, if I do force it to move, so I'm going to try and move it in such a way that it's emulating a bicycle falling over to my right. So I'm going to rotate it about this axis. If I do that, then probably you've felt this before, it turns to the right. So I'm trying to rotate it simply in this way, but it's wanting to do this as well. And you can see it even more dramatically if I just let go of all of the force here, so that it's basically hanging in this way. I want it to just fall like this. Then it goes to the right. And the same in the other direction, just in case you think I'm cheating. So why does that, I mean, that's pretty strange. Why does that happen? You can write down lots of maths, and that's an adequate explanation if you like maths. I think you can also get kind of an intuitive understanding of why that happens. If you imagine the wheel spinning like this, and you think about just a section of the wheel here independently. So this is just a chunk of wheel, and at the moment the wheel's spinning this way forwards. This piece of wheel is going that way. And it's being kind of guided around in a circle, basically by the tension of these spokes. It's happily going around in a circle, but at this point in time, it thinks, I'm going that way. It's like the tennis ball. The tennis ball is moving in a particular direction. If you want to change the way it's moving, you have to apply some force. So I'm going to apply a force. I'm going to twist the wheel like this. In doing that, what I'm doing is basically pushing this chunk of wheel off course. So now it's happily going this way. I'm applying some force, and it's getting sent off that way. Okay, so now I've pushed it off course. It's got this kind of extra component in its motion, and by the time it gets around to this part of the wheel, now that extra part is turning the wheel this way. So it was traveling this way. I've sent it off course to the right. Now it's around here, and that extra bit of rightness is turning the wheel to the right. Same for a chunk of wheel at the bottom. This chunk is coming around this way. As I push the wheel, I'm diverting the course of this chunk off this way, and as it comes up, it turns the wheel to the right. And of course, that's exactly what we want the wheel to do. We can be excited because what we want is that as the bicycle falls over to the right-hand side, we turn into the fall, we steer the bicycle to the right, and that's what the gyroscopic effect is doing for us. So we say, great, we've solved the problem. It wasn't the kind of simple gyroscopic effect, which we broke by locking up the forks. It's something a bit more subtle and a bit more complicated, and look how clever we are. We found the subtle solution. But then this guy comes along. So this is David Jones. Sorry, I just had to remember his name. So he wrote an article in Physics Today in 1970 where he took a really nice approach. It's a good approach if you want to do good physics. He went and looked at all of the kind of existing literature and theory on how a bicycle is stable and how a bicycle can be self-stable. And he's basically dissatisfied with it. It was all contradictory and incomplete and inconclusive, and the few hypotheses that were clear in that literature, he basically went through a few of them and tried his hardest to break them. The way he did that is by trying to build an unrideable bicycle. So this is URB1, Unrideable Bicycle 1. This is a bicycle in which there is an extra front wheel running in parallel with the normal front wheel. This wheel is touching the ground and is spinning clockwise from our direction, and this second wheel is spinning anti-clockwise in the opposite direction. So the way physicists like to kind of visualize the effect of this wheel spinning is that if I'm spinning it clockwise, they say, well, that's sort of like a stick pointing out of this wheel this way. And is that right way around? I can't remember it now. No, it's anti-clockwise. So it's like a stick pointing out of the wheel this way. Of course, it's nothing like a stick pointing out of the wheel this way, but you can model it in that way, and you can build a mathematical system which works, where you treat it as though it's like a stick pointing out this way. And if the wheel's spinning the other way, the stick's pointing out the other side of the wheel. If you have two wheels in a single system, one of which is spinning clockwise and the other one is spinning anti-clockwise, those two sticks, those two vectors cancel one another out, and you conclude that the gyroscopic effect should be negated, should be cancelled. And that's true. That's true. This bicycle really should have no gyroscopic contribution from the front wheel up to experimental error, but clearly this guy is still able to ride it with no hands. So what's maybe a bit more messy and fuzzy is that he said that basically you couldn't really get this bicycle to run on its own and to self-stabilize in the same way that my bike does in St. Werburgh's. But he said the fact that he could still ride this quite happily with no hands suggests that there's still something more or something missing or some composite effect. It's not just this clever effect of the gyroscope steering your wheel in the way that it should go. It's something more complicated. So what else could be contributing? Well, maybe it's trail. So what you notice about lots of bikes is, or most bikes, is that the fork here has some kind of bend in it. The bend goes forwards 99% of the time. Why is that then? You can see this fork is bending forwards. The fork and the wheel kind of rotate about an axis which goes through the headset here and up to the stem. And if you follow this axis, the steering axis down, the hub of the wheel is offset somehow from that axis. And usually it's offset that way, forwards. We call the amount of offset, well, sometimes people call it the offset, sometimes people call it the rake, sometimes people just argue about what you should call it for hours on forums. But there's generally some kind of offset like this. And what that means is that if you follow this steering axis down to the ground, you find that it's the point at which the steering axis meets the ground is just in front of the point at which the wheel meets the ground. So the wheel is trailing the steering axis. And we say there's some trail. This distance is called the trail. Why is that then? Why is that there? Some people say that it's kind of like a caster wheel. So you find these wheels on the bottom of shopping trolleys, office chairs and things like that. And here's the steering axis. This caster can rotate about this axis. And here's the wheel, and here's the point at which the wheel touches the ground, and the wheel is trailing the steering axis in the same way as a bicycle. And people say, well, this caster is kind of because it's trailing, it's gonna guide the bicycle somehow, and it's going to guide the caster rather somehow, and the bicycle is kind of the same. So you can see at least one effect, which is that this bicycle has some rake and it's got some trail, so we can actually see the trail on this bicycle. See this red line coming down here. That red line should be more or less in line with the steering axis of the bicycle, and it goes down and touches the ground just in front of the point where the wheel touches the ground. Okay. If if I lean my bicycle over to the left, then the wheel turns to the left. Why is that then? Well, some people say that if you take hold of the handlebars like this while the bicycle is leant at some angle, and I'm going to just turn the handlebars back to straight while keeping the bike at an angle like this. If you watch the top of the stem when I do that, it's very subtle, but basically you can convince yourself at home that the stem goes up when I straighten the wheel out. So the stem, or in fact the center of gravity of the entire bicycle is going up when I straighten the wheel and down when I turn it. And note that this is the turn which we want to make in order to right our bicycle. So some people say, well, what's happening is, because of this rake and this geometry, as we lean the bicycle over to the side and we're about to fall off, the bicycle wants to be as low as possible, in the same way that a piece of jam on toast wants to be as low as possible. It wants to hit the ground, it wants to reduce its gravitational potential energy. So the bicycle can drop, the only way it can drop is by drop more is by turning the handlebars. So it does, and it turns the handlebars and it corrects its fall. So maybe that's something which contributes to this self-stabilization. And lots of people actually believe that. And one thing that's really nice is that sometimes like Asda or Walmart sell bicycles, and what they like to do is put the fork on backwards. So you when you're putting the stem into the fork, you accidentally get it the wrong way around, and you end up with a bike which looks like this, apart from with the stem sticking out forwards. And people, they say, well, that's really dangerous. That's horrendous. Isn't this going to be completely reversed? It's going to be completely unstable. Well, actually, sorry, if we bring this around, you can see, first of all, I'm not condoning this, but one thing that you can see is that actually the trail, when you do that, is increased. Right? This line now is sticking out right out down here somewhere. The steering axis is in front of the contact point of the wheel, and it's in front by a bit more. So in terms of the stability, maybe the stability is actually increased in this thing. Maybe it's really dangerous because the fork isn't designed to work like that, but maybe the stability is increased. So why do they even put this rake on in the first place? As an example, you can see that this fork's on backwards. And that's generally true for these bicycles, that you put the fork on backwards. It supposedly improves the stability of the bicycle. It also allows you to get a bit closer behind your aerodynamic friend, it allows you to improve your aerodynamics by getting up closer behind the motorbike and so on. But what if we actually have negative trail? So what we saw there is that in this bicycle, if I turn the fork around, the trail increases. What if we have negative trail? So here you can see that now, actually you should be able to see it. So now if I lean this bicycle over, I'm about to fall off the bicycle to the left, then now if I turn in the right way, you can really see the stem going up and down. Okay, the effect is more pronounced. And so really you can convince yourself that this thing should, if the source of self-stability of the bicycle is this rake effect, then it should be even stronger with the fork the wrong way round. If instead we tilt the bicycle up until that red line, the steering axis, is behind the contact point of the front wheel, and it's a bit difficult to do, then as we tilt the bicycle over, it's kind of not trivial to do this. I hope I can do this. Yeah, it's not easy because I have to lift this bicycle, but basically it's steering the wrong way. As I fold the bicycle over and it starts to fall over, it's steering out of the turn or out of the fall, and it's going to be unstable. So just in case you don't believe it, there's a video of this bike running down in St. Werburgh's with the fork on backwards. There it is, it's stable, it's a bit fast. There you can see that the fork is backwards somehow. Well, I have to take my word for it, but it's you can feel that it's actually more stable when you do that. So maybe that's it. Maybe this effect that we just saw, and you can easily test on your own bike. Maybe it's the trail that stabilizes the bicycle when it's running on its own, or maybe it's a combination of the trail and this gyroscopic effect, which had some kind of convincing demonstration. This is just another one of these unrideable bicycles. This one really does have negative trail, and this was the closest that he came to building an unrideable bicycle. It was almost unrideable, but not entirely. So then comes this paper. So this was published in 2011 in Science last year, and it's a paper about a bicycle and about gyroscopic effects and caster effects and things like that. So publishing in Science is what we really want to do. Science is an extremely prestigious journal. It's like, well, it's not really like getting a top 10 record, but it's kind of somehow similar. It will do very good things for your career. Science it deals in very serious science. What is a paper about the stability of a bicycle doing in this journal when we've been building bicycles, well, for a debatably extremely long time? This is just some titles that I picked out from the same month of Science. So we have nanometer thick equilibrium films, the interface between thermodynamics and atomistics. We've got carbon-13 NMR guides, rational design of nanocatalysts via chemisorption evaluation in liquid phase, mutations in U4. Well, anyway, and then finally, why don't bikes just fall over? So what they did in this experiment is a really beautiful idea. So basically, then following on from this work, they went and did a full kind of literature review, went through all of these theories of why a bicycle can be self-stable, why it exhibits this self-stabilizing effect that we saw in St. Werburgh's, and built a bicycle which really shouldn't even be able to exploit any of those effects. So this bicycle, this is a normal bicycle, and this is the bicycle that they built. Doesn't really look very much like a bicycle, but it's still technically a bicycle. First of all, it's designed to have no gyroscopic effect. We'll get on to how they do that in a minute. Secondly, the trail of this bicycle is designed, well, the bicycle is designed such that the trail is negative, like when I had to lift my bike. So if it's exploiting that effect, then it's going to turn in the wrong way and be unstable. And basically what they show is that even if you build a bicycle like this, it can still exhibit that effect. Here's another photograph of it. So they use much the same technique to get rid of any gyroscopic effect. They have one wheel which is rotating on the ground and a second wheel which is counter-propagating and cancelling out any gyro effect. These wheels are also very small, so any gyro effect anyway should be very small. And the trail, you can see that the steering axis is behind the contact point of the wheel. And so this is Cornell University, Delft in the Netherlands, and Twente in the Netherlands. And this thing stabilizes itself even when it's given a shove. So what's really nice about this is that for this paper, basically what they did is built a kind of analytic mathematical model of a bicycle and then just solved for bicycles which are stable and yet have negative trail and zero gyroscopic contribution. They solved some equations, drew a picture, built it, and it more or less immediately worked. And their conclusions in this paper are kind of still, in 2011, not entirely satisfactory. So they wanted to build a bicycle which doesn't exploit any of those effects which were previously proposed for the self-stability of a bicycle, and they succeeded in doing that. So they've just kind of, if not destroyed, at least damaged previous theories for the self-stability of a bicycle. But in terms of actually explaining why does this bike pull itself right again? Well, they say to hold self-stable a bicycle in a steady to hold a self-stable bicycle in a steady turn to the right requires left torque on the handlebars. You can see that if you ride a bicycle, I mean, we know this, anyone who rides a bicycle knows this. If you ride your bicycle and you lean it out to the right while putting your body to the left, what you'll find is that you have to keep pulling the wheel around this way or else you'll fall off. They say there must be some coupling between lean and steer. You know, I did that in St. Werburgh's. If you stick your forks and prevent them from moving, or you, well, I don't know. Anyway, it's not quite the same thing, but it's pretty clear that there must be some coupling between lean and steer. So they really don't explain why the bicycle is self-stable, even in this paper. And it's pretty kind of astounding and interesting to me that we can still have papers which contain this kind of, or journals which contain this kind of material in 2011 and still end up with this kind of conclusions on why a bicycle can be ridden. And their final conclusion is basically that because you can build a bicycle which doesn't exploit any of these effects, perhaps there are some good bicycle designs where you don't have any gyroscopic effects or any trail or any rake in your fork. Perhaps we should all be riding some bizarre design of bicycle where the fork is completely straight or where the fork is inverted. And so I'll conclude at that point. I hope I've convinced you that bicycles are efficient. I think bicycles are kind of like this amazing museum of all of the efficient, simple machines that people have kind of invented over the last couple of decades or so. Well, sorry, more than that. But and I hope that I've conveyed some of the kind of counterintuitive behaviour of a bicycle as a machine. And yeah, I'll conclude at that point. But thanks very much for listening. It's appreciated.